The Phileas Fogg problem is you've got a room with a number of doors leading out of it. You don't know which is the correct door to take. All the others just lead to empty cupboards. Each door has a doorknob and 3 locks. A, B, and C. Suppose there are 100 doors. There are 300 keys. You need to find the correct door as quickly as possible and escape. Because I've only got a small whiteboard here, I can't draw 100 doors. So let's just say, in fact, that there are 4 doors. Door 1, door 2, door 3, and door 4. And let's suppose there are just 12 keys. Let's suppose that for door 1, key 1 goes in the first lock, key 5 goes in the second lock, and key 3 goes in the third lock. And for door 2, key 2 goes in the first lock, and so on. These are the correct combinations to open each door. Now, we're going to look at the answer state, problem state, a solution state. The answer state is the correct way of solving the problem. That's this one here. The answer state is D2, K2, K3, K7. I'm going to write it as a 4-tuple. The solution states, and I guess if there were other ways of unlocking the doors, say, so for example, D2, K1, K3, K4, then there might be 2 answer states. That's 2 ways of solving the problem. Or there might be other corridors out, then this would also be an answer state here. Okay. At the moment, we'll just have it as one answer state, but that's not important. The solution states are legitimate potential answers, though whether they are answers or not is not at the moment known. So for example, if I was to try door 1 with key 1, then key 2, then key 3, that's a solution state. It's a possible solution. It will turn out that these keys won't open. Well, let's just check. Oh, actually, we'll go to door 1. Key 1 will open the first lock. Key 3 will open the third lock, but key 2 will not open the second lock. So it won't open the door and we won't be able to escape. And in fact, if there was no corridor there, even if it did open the door, we wouldn't be able to escape. But from simply looking at it syntactically, it looks like it could be a solution, so we call that a solution state. How many solution states are there? Well, you've got a bit of wiggle room here. It depends how you represent a solution state. The naive way of representing a solution state is the way I've done it here. It's a 4-tuple. The first thing is the door number, then a key, then a key, then a key. This is for locks A, B, and C in turn on each door. So how many possible solution states are there? Well, there's 4 doors. There are 12 keys that could go in each lock, assuming perhaps that the same key can be used twice. So there's 4 times 12 times 12 times 12 possible combinations. There's, let's see what that is. 12 times 12 is 140, so 150 times 10 is 1,500, say. Times 4 is about 6,000. So there's something like 6,000 possible solution states. And if we were going to brute force the problem, when we brute force, we simply enumerate over all the solution states. So a brute force would take us, in the worst case, 6,000 attempts. In the best case, we'd luckily try the correct one the first time, and it would only take us one. On average, it will take us, if we have no more information than that, and we're essentially trying them in a random order, or the solution is essentially random as far as we can see, then on average we'll find it halfway through. So after about 3,000 attempts of examining the solution states, we'll find which one of them is in fact the answer state. Notice if there were no answer states at all, then to be able to answer the question, is there a way out of the room, we'd have to consider every single solution state. With only one solution state, we'd have to consider half on average, or all of them if we're unlucky, and with two solution states, we'd consider a third on average, and so on and so on and so on, before we find the first state. If we just look at the brute force way of solving the problem, with 6,000 combinations, it's a legitimate approach for a computer, but for a human being with fingers and keys, it would be very annoying to have to try 6,000 things. So probably for a human, unless there were extenuating circumstances, I reckon I'd call that an infeasible solution. With brute force, you're essentially going through all the solution states one at a time. The risks with brute force is that you overlook one. Don't do that. So it's very important to be systematic in the way in which you go through the solution states, and often the way you represent them gives you a clue as to a systematic way of going through it. For example, you could simply just combinatorially go over them all, try fix that, try all combinations of that, try the next combination of that, for that, try all combinations of that, try the next combination of that, for that, try all, and so on. And we could just systematically go through it that way. It's very important to be systematic though, when you write your brute forcer. That's probably the biggest trap, and how you'll fail is you'll just accidentally, through poor representation or poor, a poorly written program or poorly thought out program, you might accidentally miss some of the states and not look at them. And of course, that's not a disaster if the answer doesn't lie there, but it is really annoying if you get to the end and you've looked at them all and you happen to have overlooked one of the solution states, one of the solution states that is an answer state. All right, but assuming you write a correct program and you're not going to overlook anything, there's probably only two things to say about a brute force. One is for each of those 6,000 attempts, you'll be doing some work, so make that bit of work as small as possible, because you're going to have to do it a large number of times. And notice this won't change the complexity of the solution, it'll just change the absolute amount of time. The only other interesting thing I can think of to say about a brute force is if the thing you're trying to do is find an answer, one answer state. You're not trying to find them all, say any solution will be good enough for you, then the order in which you consider the solution states as you go through is pretty important. If at all possible, you should select an order where the answer is more likely to occur sooner than later, so you can give up, because of course you can stop looking as soon as you find a solution. So if I was searching my house for something in a systematic but brute force way, that would correspond to me looking in the most likely places first. I still have to look in every place if I can't find them there, so it's still a brute force search, but if I look in the most likely places first, then perhaps I can cut the search slightly shorter. That's probably your biggest potential area for using your brain to speed up the search. Okay, so we're looking at the Phileas Fogg problem. Remember, answer states are what we call the actual answer to the problem. Solution states are possible answers. We test them and see if they are answers or not. We've just looked at brute force. Brute force consists of going through all the solution states and testing them. But if there's too many of those, that's not a viable strategy. So let's look at some other strategies. Now, the nature of some problems, and the nature of this Phileas Fogg problem that we're talking about, with the 4 doors, each door having 3 keyholes, each A, B, and C, and you've been given 12 keys 1 to 12, each door being unlocked by a combination of keys. You don't know them. One of the doors leads to freedom. You want to get to freedom. How much work do you have to do? Well, the solution states, as we saw before, are all combinations of all doors with all keys. So here are some here I've written out. Door 1, key 1, key 1, key 1, or door 1, key 1, key 1, key 2, or door 1, key 1, key 1. And so, for example, this one here means try door 1 with key 1 in lock A, key 1 in lock B, and key 3 in lock C. Now, I've written here the correct keys which open each lock. So you can see in this example here, in door 1 we need keys 1, 2 and 3 in locks A, B and C respectively. So we're going down here trying all the combinations, and eventually we'll find how to unlock door 1, and this keeps going with door 2 and then door 3 and then door 4, and as we said before, there's about 6,000 of them, about 1,500 for each door. I just put this one close to the top so I didn't have to draw along. I was too lazy to draw 1,500. So yeah, 1, 2, 3, what sort of combination is that? That's the sort of combination an idiot would put on their suitcase, isn't it? Okay, now 6,000, that's too many. Can we cut it down? Can we not actually have to exhaustively, brute forcedly search through every possible solution state? Yes, in this case, for this problem we can, as we talked about before. Although deciding which door to pick is not an easy thing to do. Once we've picked a door, it's actually much easier to unlock it than trying all possible combinations. Assume that each key fits in each lock, each key turns each lock, and there's some sort of, say, audible feedback when you've unlocked it. You hear a clicking sound. In that case now, the problem to work out the key to unlock lock A, the second problem, the problem to find the key to unlock lock B, and the third problem, the problem to find the key to unlock lock C, are 3 sub-problems of the big problem. The fourth problem, which door to open, is an interesting problem. We'll put that to the side for a minute. So given that we've decided on a door, we could try all 1,500 possible combinations of all the keys, but because the 3 problems I talked about before turn out to be independent of each other, so you can solve each of them not thinking about the others, there's obviously a much faster solution, which is let's see what I'm actually doing as I'm unlocking it, and it will come to you straight away what I'm trying to say. I go to door 1, I stick key 1 in lock 1, and I turn it and click, I hear it unlock. I take the key out. I put it in lock 2. I turn it. I don't hear a click. It hasn't unlocked. I take it out. I put it in lock 3. I turn it. I don't hear a click. It hasn't unlocked. That's because I need, key 1 in the first, key 2 in the second, and key 3 in the third. So now I go down to the second one. I try key 1 in lock 1. Click. I hear a lock. It unlocked. Let's suppose I relocked it after I left that example. So on and so on. Now you can see, as soon as I realize on this first go here that the second key does not unlock the second lock, there's no point in trying all these other combinations going down here because none of them are going to work. So this thing that has this vast number of states, I actually don't have to consider all those states. I don't have to try them all. Let me draw a picture and show you why not. Here's what I prepared earlier. Suppose we just have 2 locks. Let's simplify the problem even further because I couldn't draw enough to fit 3 on. Let's say lock A is all these these are all the possible keys we could try and lock A. Here are all the possible keys we could try and lock B. You can see that if there's 12 here and 12 here, there's 12 squared, 144 combinations of keys to try and lock A and B. You know that already, right? That's sort of obvious. Now, the interesting thing is that the sub-problems, working out how to unlock lock A and how to unlock lock B, are completely independent of each other. So there's no point well, let's look exactly, here's what I'm trying to say. Suppose I tried, what are my correct combinations here? In this here, we're saying key 9 is for lock A, and key 5 is for lock B, will unlock lock B. I'm trying an answer state here. I'm trying a solution state here. Oh, it doesn't work. I stick them both in here. I try it. Oh, it doesn't work. I stick them both in here. Oh, I find that the first lock A, is unlocked by key 9, but the second lock B, is not unlocked by key 6. So I've just tried 9, 6, and I've got partial success. Now, as soon as I do that, I know the solution has to lie in here somewhere. Oops. So I don't have to consider any of the rest. I can now solve this problem. I've projected the problem. onto one less dimension, as you can see. Essentially, what we can do is we can try all of these keys in turn, not even trying a pair of keys. We could not even attempt to solve the problem with 2 keys. I could simply do an experiment where I tried the keys one at a time in the first lock, in lock A, and see which one unlocks them. Because I'm not trying 2 keys, it's not a possible solution to the problem. It's a partial solution to the problem, which we call a problem state. It's a partial solution state. So you see, I'd simply have to try all 12 keys in lock A, then all 12 keys in lock B. So I do 12 plus 12 in the worst case tests rather than 12 times 12, which is to do all possible combinations. So if the problems are independent of each other, we can turn a times into a plus, and that's really neat. Okay, that lets us be greedy. And greedy simply means we solve each of the sub-problems, and that solution we then assume is part of the solution to the big problem. And if a problem is of a sort that a greedy algorithm works, that makes us very, very happy because they're fast, because of turning the timeses into pluses. Okay. So the cool thing about the greedy method is we construct the answer state bit by bit, rather than searching for it amongst all the solution states. Now in the door problem here, I can use the greedy method to solve the problems of which keys go in which locks, but I can't use it to solve which door to open. That's because the door is very, and the locks are strongly dependent on each other. If I find, say for example, on the first door that key 1 unlocks the first lock, when I try 2 and 3, suppose I try 1, 1, 1, I find that key 1 unlocks the first lock. I know now that key 1 will unlock the first lock for all other combinations. It doesn't matter. I never have to test that again. It's just fixed. It's not going to change no matter what other combinations of lock I try over here, keys to locks I try over here. This solution I can just pick now and freeze and commit to it because it's not going to change. But you see, I can't do that with the door. If I change which door I'm looking at, then it completely changes the behavior of the keys. There's a great dependence between them. And if I find that the first key unlocks lock A in door 1, but suppose I change the door 1 to a door 2, well, now the first key might not and probably won't unlock the first lock in door 2. So there's this dependence on them. They're not independent sub-problems that can be solved in that way. So although I can solve the lock problem, I can't solve the door problem. Nonetheless, greedily solving the lock problems gives me the unique answer state for the sub-problem. And now I just simply have to brute force. I try all 4 doors. I can unlock them all. Do they open onto a cupboard or do they open onto the passageway? Well, I have to try each one of those in turn. Okay. Similarly, the coin problem. Do you remember the coin change problem? A solution state. It's simply how many $50 notes are there? 7. How many $20 notes are there? 3. How many $10 notes are there? 2. How many $5 notes are there? 0. How many 50-cent pieces are there? 0. How many 20-cent pieces are there? 1. How many 10-cent pieces are there? 1. How many 5-cent pieces are there? 1. Okay, so the vector 7, 3, 2, 0, 0, 1, 1, 1 is a possible solution to the greedy change problem. And you can see how many solutions there are. Well, there's an awful lot of them, in fact. There's as many possible combinations of 50s as I can put in, as many possible combinations of 20s, as many possible combinations of 10. So this vector here is a solution. And because the coin change problem, the way we stated it, was solvable greedily, because it means that these sub-problems are independent of each other. So I can work this number out here independently of this number and the solution for here, 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 and here. So if I wanted to work out how to produce, I don't know, $82.15, I'd say, well, there's got to be one of those. There's got to be, and I can work that out without knowing anything else. And then I subtract the 50 off here, and that tells me there's 32 left, which tells me there's one of those. I subtract that off, there's 15 left, which tells me there's one of those. 0 of those, 15, I've got to find 15 cents now. That's 0, 0, 1, 1. That looks binary, doesn't it? Of course, it won't always be binary. It won't always look like that. So I can solve each of these subproblems, a problem of how many 50s, a problem of how many 20s, a problem of how many 10s. They're independent of each other if I solve them in a particular order. And that's what permits me to use a greedy solution to this problem. So now let's consider the order issue. With the door problem, it didn't matter what order I considered the lock subproblems in. I could try lock C first, then lock B, then lock A, or I could try lock A, then lock B, then lock C. It doesn't make any difference. I'm going to do the same amount of work, 12 plus 12 plus 12. However, in the greedy one, obviously I've got to consider them in a certain, the coin problem, I've got to consider them in a certain order. Okay, so we're solving the subproblems in turn to build the answer state that we need. But in what sequence do we solve them? We solve for the coin problem, it matters. For the Phileas Fogg problem, it doesn't seem to matter. The order is well worth thinking about because sometimes it can make a huge difference. Let's consider now a variant of this problem where the evil person who's locked us in the cellar has noticed that on average we only need to try 6.5 times, I mean somewhere between 1 and 12, so on average 6.5 times in each lock to unlock it with the 12 keys. And it's only in the very worst case, when we're really unlucky, that we have to try all 12 keys in a lock and the 12th one unlocks it. And the evil person who's locked us in this cellar has decided that they would like us to experience going to 12 more often than the average case of than we go to the average case of 6.5. They laugh evilly. They're watching us on camera when we have to do 12. So they want to make us do more work. So what they do is they say, ha ha ha, lock C. Sometimes lock C won't have a key that solves it, and sometimes it will. Of course it will for the actual answer, but maybe over here there is no key that solves lock C. And maybe here there's no key that solves lock C. Now, they're thinking, oh, I make them do more work now. When they are evaluating these doors, they'll have to try all 12 keys before they realize there is no solution, forcing them into the worst case. But actually, they're not being as effective and effectively evil as they thought, because sure, we'll have to do more work if we consider the locks in order A, B, C. But what about if we now consider the subproblems, the unlocking the lock problems, in the reverse order? What if we consider doing them in order C, then B, and then A? I wonder if you can see the advantage here. Let's suppose we're checking door 3 for some reason. How many comparisons, how many times would I have to do? I have to do 12 tests, followed by 10 tests, because if I'm trying the keys in order, the 12th key, it's unlucky for me, it's the 12th one. So 12 plus 10, and here I'll have to do 12 more. So that's 34 tries I have to do. However, if I did them in reverse order, and I tried here first, I'll still have to do 12. I'm doing it in the other order, I have to try 12 keys for the first lock, and I find that none of them open it. Now, can you see I can stop now? If there's no key to unlock door C, lock C on door 3, then I can never open door 3. So it can't be the solution, so there's no point in trying these two here. So what we see is that if we adjust the order here, it's letting us fail early. If the problem has a constraint like this, it lets us detect early failure. It lets us fail early. And by failing early, it saves us from having to do work. Here I only have to do 12. Here I only have to do 12. This saves 9 for me. It saves, what? It saves 22 for me here. It doesn't save anything here or here. Okay. So, but still, it's saving me work. Now, this is an interesting idea. We're going to exploit this next. Even if we don't have the lovely structural property of the independent property of the problem that lets us solve it in a greedy fashion, and so cut down, not have to search through the search space, but instead just construct the answer step by step. Even if we don't have that, even if we construct the answer step by step, perhaps if we look at the order in which we construct it, which step we do first in the step by step, and which step we do second, and so on and so on, maybe this will let us give up early. And by giving up early, there will be states that we don't have to consider because we know they can't possibly work. Because you see, in a case with a huge number of solution states, if there's too many solution states to brute force, then really what we have to do is not look at every solution state. It's as simple as that. But how can we determine which ones are safe not to look at? Well, by early failure, we can sometimes, here we found 22 things that we didn't have to consider. All right, so we're going to exploit that trick next using a method called backtrack. Okay. Let's consider now that we only have 3 keys, because this gives us a branching factor of 3, and I couldn't fit more in the whiteboard. Let's suppose we've got 3 keys. We've got 3 locks, and we're going to consider them in turn, A, B, and C. A, B, and C. And we've still got our 4 doors initially. At the bottom here, I should have all, well, if there's 3 times 3 times 3 by 4 doors, 3 threes are 27, by 4 it's about 100, isn't it? So I should have at the bottom 100 possible solution states. This solution state here, for example, just so you can see it. This solution state here corresponds to picking door 1, trying key 1 in lock A, trying key 2 in lock B, and trying key 3. Oh, this is our 1, 2, 3. Trying key 3 in lock C. And so this one here corresponds to doing picking door 2, in the first lock trying key number 3, in the second lock trying key number 2, and in the third lock trying key number 1. So you can see there's 100 of these down the bottom, approximately, whatever 27 times 4 is. So maybe closer to 110, isn't it? Let's say. Now, there's 110 states down the bottom. Previously, we were just jumping to a state and trying it. So I was trying all the lock, putting the key in, putting the key, picking a door, putting the key in, putting a key in, putting a key in, and trying it to see if it unlocks. Put a key in, oh, sorry, pick a door, put a key in, put a key in, put a key in, and try it. And there's, every time I try it, if I put a little blobby there, I'm going to try it 110 times. I'm going to do it, check, I'm going to do a bit of work, the try it work 110 times, once for each possible solution state. Previously, when we're doing the brute force, what we'd do is we'd skip straight to the bottom. We wouldn't worry about the tree structure here. The tree is arising because I'm picking the door first, then I'm picking the key for A next, then third I'm picking the key for C, lock B, and then finally fourth, I'm picking the key for lock C. I'm doing them in that particular order. But the brute force doesn't care what order you pick them in. In the brute force search, I just noticed there are 110 of them, and I just went through all those 110 in sequence. Who cares the order in which I built up those solution states which contained a door? So for example, we pick this one here, door 1, key 2, key 3. Here I wrote them from left to right, but I could have written them right to left or in any order I wanted. Who cares? When you're doing a brute force search, you just care about the final thing at the end. Boom, boom. But as I'm filling them in slowly, with 2 things not determined yet, I've got what we call a problem state. This is, I've picked door 1, I've picked key 1, I haven't yet picked any of the other keys. So at that point, I'm here. How many states are there? Well, all the internal nodes of the trees, plus and the root and all the leaves forms all the problem states. So you can see there's more than solution states. Previously, when we did a brute force search, we did a bit of work for every solution state. It turns out, if there's too many solution states, so that's too much work, you can actually often save time by considering every answer state and doing a bit of work for every answer state, even though, ironically, there's more answer states than there are solution states. Here's how it goes. Again, consider our doors with our 3 locks in them, A, B, and C. And a doorknob, very low doorknob, it's for midgets, this room. A doorknob at the end to try to see if you've unlocked it. Let's suppose each key goes in each lock. Any key can fit in any lock. All keys turn in all locks, but when you unlock the thing, it makes a clicking sound. Now, this is the greedy solution we saw before. What we do is we pick a door, we try, we consider it has 3 children, possible children from this answer state here. This is the answer state we're in now. I generate each of the 3 children in turn, and I notice if there's a click. I do a test here. Did I hear a clicking to get here? No, yes, I did. No, I didn't. No, I didn't. Okay, because I didn't hear the click, that means it didn't get unlocked. It means I can lop it here, and I can lop it here, and that means I never have to consider these answer states here, and more particularly, I never have to consider all these solution states here. Similarly here, I get to this node here, I generate all its possible children, dump, dump, and dump. I listen in each case, and no click, click, no click, aha. So I can lop here, and I can lop here. And now I only have to consider these three. Listen for the click, boom, I've got it. Took a lot of more work to get here than previously. In the brute force solution, I just jumped here directly. Now I had to do work along the way, but that little work has saved me so much. Look, it saved me having to consider all those other states there. Well, how many of them are there? 3 times 3 times 3 is 27. So, saved me 26 of them. I only actually end up generating one of them. That's how the greedy looks in a tree. Now, suppose we aren't able to do a greedy. Suppose, for example, although the lock clicks when you try the right key in it, it also sometimes clicks when you put the wrong key in it. It doesn't unlock, it just makes a clicking sound. How annoying is that? That means hearing a click doesn't give us certainty that we've unlocked it. So I can't solve the problem greedily now, because greedy means sort of essentially I never go back. Let's have a look what would happen. I could go down to A, I generate its 3 children, 2 of them have clicks. So now I think, oh, well, maybe the solution for A is this one. I go down here, maybe one of them has a click. I follow him down, I go down here, has a click. I turn the doorknob at the end. Oh, the door doesn't unlock. One of those clicks at least was tricking me. I have to go back and try all the other combinations. And after I've tried all the other combinations in here, eventually I go back here and think, oh, well, maybe it was the click that went down here that was the correct click. So you can see I've sort of backtracked. I've had to go back. I've had to undo my initial decision, which was that the solution for A may well be, lock A may well be key number 2. And instead I'm saying, well, no, actually it's key number 1. So that's not greedy. I wasn't able to determine whether it was right or not until I'd solved all the other subproblems, and then I found it wasn't right. So it's not a greedy, but all is not lost. Actually, it can still be pretty good. Let's consider which are the possible ones. I come down to A and I generate all the children. These 2 here maybe. I generate all 3, but this guy doesn't click, so I prune him off. Pruning here is called pruning when I lop a tree off, or sometimes it's called bounding as well. And you run a bounding function to work out if you're going to bound it or not. The bounding function here is simply listen. So I have to run the bounding function as I go down all the time. I didn't have to do that in the brute force. It's more work, what a pain. But still, it's only a little bit of work to do the bounding function. And here, look, it already saved me. That listening saved me so much work. It was well worth it. The cost of the bounding function is more than repaid in the reduction in the number of states I have to consider. So I now have 2 children states. I have to determine, I'll expand, maybe I'll expand all 3. And I discover that this one didn't click, this one did click, this one did click. And I go down one more level. This one clicked, but these 2 didn't. That was good. And going down here, this one clicked and those 2 didn't, say. So you see, it's the pruning, the bounding has eroded the tree. I now only have this red tree to consider. All right. Oh, what did I say happened here? Oh, that's pruned, so I never go down there. Oh, it looks like there's only 2 possible paths to the bottom. So the pruning, oh no, hang on, I haven't done this one here. So let's suppose this guy had a path here and a path here, and that one didn't work. And let's suppose none of those worked, but 2 of these ones worked. So maybe I've got 4 paths to the bottom. Out of 27, that's not too bad. The bounding function saved me a whole lot of work. How do I actually carry this out? If I carry it out one way, it's called a backtrack. If I carry it out another way, it's called a branch and bound. Here's how a backtrack works. Backtrack is pretty mindless. You always take the leftmost one, say, first, and you just keep going down as far as you can till you have to go back. And then when you come back, you come back as little as you can. So I go do-do-do-do-do, I'm going to do it in blue. Here's my journey. I come down here to the considering door 1. I try this guy first. Does he click? Yes! Okay. So now I'm here. I'm not going to go back and generate the other 2 children. I'm going to stay here. Now I go down here. Does it click? No. Okay, I go back. I'm backtracking. I come down here. Does it click? Yes. Oh, my solution's here, isn't it? I'm going to find it really fast. Or let's suppose it wasn't here. Let's suppose my solution really was over here somewhere. Maybe the solution's here. So you can see how the backtracking works. If I get to the answer too quickly, you'll never get to see how I undo my mistakes. Let's have some more mistakes. So I've come down to here. I've come down to here. I tried them all one at a time. But if you remember, none of them clicked. So I go down here. No, it didn't click. So I go back. I'm going to go back as far as I can, as short as I can, which is to here. Go down, try it. No, go back. Short as I can is to here. Go down, back. Short as I can is to here. But there's no more children to consider here. So I have to go back one further. So I was forced to go back 2. But I'm not going to go back 3 because there's still more children to think about. So now I try the next child here. And there's a click, yes, so I keep going. Down to here, there's a click, no, so I go back. Down to here, there's a click, no, so I go back. Down to here, there's a click, yes, there is, da-ding. So I'm at the end, a potential answer. It's a solution state. So I try it, open the door. What a disappointment. Door 1 leads to a cupboard. It's not the answer, so I have to go back. So to here, I actually now know that door 1, although I know it, the way I've specified the backtrack is I'm only backtracking on not hearing a click. I should also backtrack on opening the door and discovering a cupboard. But nonetheless, let's not say that. Let's say I'm only backtracking on clicking, just so you can see the path of the backtrack. So now I come down here, click, good. Down here, click, no. Down here, click, no. Down here, click, yes, yay, it worked. But try the door. Unfortunately, it doesn't. It opens, but only to a cupboard. So go back up, back up. All right, now I've gone up 2, but here, there's no more children, so I go back 3 up to here, and similarly I go down here. So does that make sense? You're going as deep as you can and backtracking as little as you can each time. The nice thing about this is it's a very simple journey you're going on, undoing as little as much as you can each time. Systematic, it will be systematic, it will go through the whole tree. And if you've got a good bounding function, a good pruning function, you can often prune vast amounts out of the tree as you go. So hopefully you don't end up going to the bottom very often and you save all that multiplication of states that happens towards the end there. So that is a backtrack algorithm. Okay, I guess the other thing to talk about is a branch and bound algorithm. So that's a backtrack algorithm. It's very, very simple. Now let's look at a branch and bound algorithm. Okay. This is very, very similar to a backtrack. We're going to do the same sort of thing as a backtrack, but we're just going to take a different journey through the tree. We're going to prune the same things and do the same lopping and have the same bounding function. We're just going to take a different order of paths. We're going to go through the paths in a different order and do work in a different order to the work that we did in the backtrack. Backtrack is very simple to implement, and that's really nice. So it gives you a good speed up. Branch and bound, we do a little bit more thinking about the path we're going to take. And so more thinking is more time. Yeah, it's more work. But in the cases where that thinking has a big payoff, this can massively outperform a backtrack. So, but in the cases where it doesn't, you might as well just do a backtrack. Avoid the extra overhead of a branch and bound. Here's how branch and bound goes. Branch is, well, the 2 steps you heard me saying while I was doing the backtracking were essentially branching and bounding. You start with a node. We're going to start here. I'll be a sort of reddy black color now. You start with a node and you generate all its children by going down all the branches. This is the branching. So I've generated all 3 children. They're only partial states, they're answer states. This one here, for example, looks like this. D1, nothing, nothing, nothing. This one here is D2, nothing, 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 and D. Yeah, generate all 4. Now you've got all 4 answer states, you whack them in some sort of data structure, queue, a heap, whatever you want. And then you pick the most, and then you pick one of them according to some rule. Now this rule is how you customize the branch and bound. You might say, oh well, first in, first out. And you can see that's going to give you a depth first search. So it's going to look exactly like a backtrack, except you've got all this extra work you've done. Or you might say last in, first out, in which case you're essentially doing a breadth first search through the thing. Or you might say more fancy things, and it's the more fancy things that are the exciting ones, like an LC search, for example, that we'll see in the last week. Okay, so we've generated these 4 children, we've put them in some data structure, and now we pick one of them. Let's suppose it's, well, that's not, in the backtrack we picked that one first, didn't we? And notice in the backtrack we didn't generate these other ones yet. We just generated them one at a time. Here I generate all the children, and I apply the bounding function to them all if you want. I can do it now or later, Might as well do it. Oh, well, it's probably better to do it later. Well, doing it now has the advantage that I prune the number of children I generate, so I put less things in my data structure. So if my data structure is going to fill up, or it's slow to put things in there, then that's a really good thing to do. But I'm going to keep going until I find the answer. At that point, there'll still be a whole lot of children living in the data structure that I won't ever get to. So I sort of wasted my time running the bounding function of those when I put them in. In that case, for those ones, it would have been better if I'd been lazy and only applied the bounding function when I pulled them out. That way I'd never have to apply it to nodes that I wasn't going to consider. But to make it simple, let's say I consider the bounding function first. So I generate all 4 children and I apply the bounding function to it. Now there is no bounding function for the doors, which door you pick in this problem. All doors are equally likely candidates. I can't rule any of the doors out. So the bounding function, there's no bounding function for that. So now in my data structure, I've stored these big blobby things. And I pick one of them. Let's suppose I'm picking, I don't know, whatever the rules are, this is the one I pick. Then I generate all its children. Branching, generating 3 children. Apply the bounding function to them. Did I get any clicks? Well, it turns out I didn't get a click there and I didn't get a click there. So I've only generated 1 child. I throw it in the data structure and I take this one out. So the data structure now contains this guy, this guy, this guy, and this guy. I shouldn't have put blobbies there. I'm only going to put blobbies there when I put them in the data structure. So I've only got 4 in the data structure now. Which one do I pick? Well, suppose I pick this one now. I expand its children. And which ones click? Suppose those 2 click and that one doesn't. Now I've put 2 more things in the data structure. And I bounded that off. So now my data structure contains 1, 2, 3, 4, 5, 6 things. And I pick the next most, I pick the one that I'm going to pick. I'm not telling you the rule that I used to pick them yet. That's because there's a million such rules. So suppose I pick this one. I want to go down. So we pick this one and we expand its 3 children. And suppose I can bound 2 of them. I only get 1. That's him. And now he's out of the data structure. And now I've got how many? 6 in the data structure still, I guess. 1. Did I ever expand? I haven't expanded him yet. 1, 2, 3, 4, 5, and 6. Oh, hang on. No, I'm considering him now. So I've only got 5. 1, 2, 3, 4, 5. I've only got 5 guys in the data structure. Now I'll expand this one. Maybe I expand him again. I try all 3. None of them work. Boom, 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 boom. Backtrack. I mean, I don't backtrack. I just take him out of the data structure. There's nothing to put in the data structure now. If none of them worked, maybe I could bound them all. So now I've only got 4 things in my data structure, and I keep going like that. Now you can see I'm slowly rippling down as I consider each guy. I haven't yet considered his children. As I generate each child, I don't generate the children of the children, but when I consider the node, I generate their children. So slowly I'm filling the whole tree in. I'm just doing it in a particular order. Now, where the payoff comes for branch and bound is you find a good order that leads you to the solution as early as possible in the search, so you don't have to bother getting to the bottom very much. Hopefully you tease it out so you hit the solution quite quickly. Examples of that are the 15 problem and things like that, which we talk about separately in the lecture. I won't say any more about branch and bound now. I just want you to understand how it differs from backtrack and how backtracking works.